Down here in the corner, we have kind of a popular picture of what an atom looks like, nucleus with the electrons flying around. But as we work on things more, we find out that the electrons are waves and standing waves. So we call these guys orbitals. So the orbitals are the standing waves of the electron. We kind of want to see, well, what do these waves look like, or at least how do we visualize these according to quantum mechanics? And last but not least is that there are some variables involved in these wave equations, and those are called the quantum numbers. It all starts back in the hydrogen spectrum. So when you have the hydrogen spectrum in a gas discharge tube, the electrons are excited, and we see things like a red line, we could see a blue-green line, there was a blue-violet line, and a violet line. And Bohr went through and said, okay, the electrons exist in different energy levels, and we had like the n equals 1 energy level, and the n equals 2 energy level, and 3, 4, 5, 6 up to infinity. And when an electron drops from a higher energy level to a lower energy level, it gives off some form of light. And it turns out that the ones we can see are the ones that drop down to level 2. So 3 to 2 is the red, 4 to 2 is the blue-green, 5 to 2 is the blue-violet, 6 to 2 is the violet. Other ones that drop down here are too high of energy to see, UV. Things that drop down to here are too low of energy, infrared. When we try to explain, why can the electron only have certain energies, well, then we actually have to go to waves. Waves are situations that can have only certain energies, and standing waves. So we looked at the waves from, let's say, a string, or we did a telephone cord, and when we wiggle it back and forth, we can get where there's one, standing wave, or one, big pattern, and we have a 2-lobe pattern, a 3-lobe pattern, and a 4-lobe pattern. And only certain patterns are possible, because that's the only way you can get a standing wave pattern. Well, that also happens in two-dimensional objects, like in this drum head. And a drum head, you can see we have a circular node here, or we have a linear and a circular node, or two linears and a circular node. Just all different kinds of patterns that can happen. Well, when we get to the electron then, the electron can have certain patterns as well. We can see that this idea here kind of helps us visualize maybe how an electron can wave. It doesn't look anything like this, but we could see that we could have one lobe, or we could have two lobes that can fit on this pattern, or we could have three lobes, so we can see in and out, in and out, in and out. So we can have different kinds of wave patterns, around the central nucleus. So, to kind of harken back to when we were talking about atoms, we said atoms, kind of like a little solar system. The electrons orbit. And so when we talk about, the wave patterns of the electron, then we call them orbitals. And the orbitals could be, when he's in wave pattern 1, then that's low energy. And then if we get to a higher energy, it's just a different wave pattern, Now, the kind of waves that we're talking about are called probability waves, and that's very odd. And what happens is if you put variables into the big wave equation, you end up with something that looks like a curve like this. And what we interpret that is say that there is a high probability of finding the electron close to the nucleus, and the farther out you get from the nucleus, the lower the probability is of finding this. And this is the lowest energy wave pattern, called the 1s. And we can interpret that, let's say that the nucleus was right here in the center of this atom. And if we took thousands and thousands of pictures of the hydrogen electron, then we would find out that very often we're going to find it close to the nucleus because we have such a high probability. And as we get farther and farther out from the nucleus, we get less and less in chance of finding the electron. And it kind of looks like this. Now, this is a little bit difficult to deal with. We certainly wouldn't want to try to draw these pictures all the time. So we usually say, well, let's just make a surface in which we could find the electron 90% of the time. So this would turn into a picture like this. We have a spherical orbital. So the chance of finding the electron somewhere in the sphere, about 90% of the time, that's a pretty good way of interpreting how this looks. Now, one of the ideas here, when we get to higher and higher energies, then we have a situation where the patterns can change. So let's say that we were talking about this first pattern. Let's just call this A energy, and we can see that what we get is we get a circular node. Well, this one here is a higher energy wave pattern, and this one is also a higher energy wave pattern. And when you get there, we can see that we have two nodes. We get a circular node and a linear node, or it could be going with two linear nodes. So instead of one node, we have two nodes. So this is slightly more complicated, higher energy, and when we get to higher energy, then we get more ways to wave. In the same way, we could call this a C wave pattern, C wave energy, and when we do this, now we have linear node, circular node, or we have three linear nodes. So we can see that there are different ways to wave. And this last one here, we could call that energy D. And you can see that that has four different linear nodes. And there would be a lot more complicated patterns with circular nodes and linear nodes. But the idea is, the higher the energy, the more ways that there are for this to wave. And that's going to happen with us in the hydrogen electrons. Now we use kind of an analogy for this. And the analogy is a little hotel. And the hotel is kind of a weird hotel because as you go up, you get more and more and more rooms. But in the very first low energy, we're going to find out that we only have one way to wave. So there's one orbital, okay, and that is the s orbital. When you get to the second level, where n equals 2, we have two different ways that we can wave. Okay, we can wave in an s-type orbital, or we can wave in a p-type orbital. And it turns out that there are three different orientations for that p-type orbital. When we get to the next level, 3, there are three ways to wave. Okay, we can wave in an S pattern, we can wave in a P pattern, or we're going to find out that there is a D pattern in which we can wave, and that has 5 orientations. So our analogy, our hotel analogy, is, we say that for each floor, and we call that a shell when we're talking about the atom, for each floor, there are different subshells. There are different types of rooms. So on our first floor, there's only one type of room. It's a suite. On our second floor, there's two types of room. There's a suite and there's a penthouse type room. When you get to the third floor, there's 3 types of rooms, suite, penthouse, and deluxe. Fourth floor, we get suite, penthouse, deluxe, and the fantasy rooms. When we get to the level 5, there are going to be 5 types of rooms. 6 will have 6 types of rooms. 7 will have 7 types of rooms. And it doesn't really get too complicated, we're going to find out, because we don't need all of these different types in order to do most of our atoms. The orbital is our individual room. So we could say when n equals 3 that there are 3 types of rooms, okay, 3 subshells in n equals 3, and if we count them up, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. We can see that there are n squared, 3 squared rooms available. Now, what do these other kinds of places look like? We saw the S and how that looks. That kind of has this spherical shape. In fact, some people say S means spherical, or stands for spherical. Officially, S, P, D, F, those designations mean something about the old spectra. There were sharp lines, there were principal lines, there were diffuse lines, and there were fundamental lines. And the SPDF now really means very little. So we do have the S are kind of spherical orbitals. The p orbitals, okay, have 2 big globs to them. Sometimes I draw it like this, this, and this. Okay, so we have a glob over here and a glob over here. And it might be along the x-axis, it might be along the y-axis, it might be along the z-axis. So the fact that we have 3 different p orbitals is because of their orientations. So all we'd have to do is take and turn this orbital different directions to get the 3 different orientations. When we get to a d orbital, okay, a d orbital sort of has a cloverleaf shape. It has 4 big blobs like that. And those 4 big blobs could be between the x and the y-axis, could be between the y and the z-axis, between the x and the z-axis, right along the x and the y-axis or oriented along the z-axis. And when you orient along the z-axis, the shape is a little different. It's sort of as though you were holding it to the orbitals here and here, and then you spun it around very quickly, and you end up with kind of an odd orbital that has a blob up and a blob down, and then there's sort of a donut shape around the middle, and you see this quite often. So 4 of the d orbitals sort of look like this, and 1 d orbital looks like that. It's called the z squared. When you get to the f orbitals, it's more complicated, and so sometimes we say, well, s is spherical, okay, p perpendicular because there's one along the x, one along the y, one along the z. Okay, d, maybe you could say diagonal, because the 4 things are diagonal to each other, and f is so weird you say forget it. Now if we really want to kind of see all these orbitals in one place at one time, here's a nice picture that I found on the internet. So on the first level here we have an s orbital. Now on the second level there's an s orbital and there's the 3 p orbitals. Now the s orbital has some inner complications. It has a nodal sphere in there, but from the outside it looks the same. When we get to the third level, then we have S and we have P and we have D, and again we can see what's happening. Here's like the sort of 4-leaf clover. Here's sort of 4-leaf clover. Here's a 4, here's a 4, but here's the one with the little donut in the middle. And we get to level 4, we have 4 ways to wave. So it could be an s orbital, we could have 3 p orbitals, 5 d orbitals, and then we have the 7 f orbitals. And kind of you can see this looks like 1, 2, 3, 4, 5, 6, 7, 8 little balloons stuck together. Or we might have 6 balloons stuck together. Or we might have a situation where we take the 8 balloons, we grab it at both ends, and we spin, and we get 2 donut-shaped orbitals here along that axis. A little odd. Now, if you really want to get into the mathematics, which we absolutely positively do not at this level, AP, but here for college, this is from Drexel University. Here they're showing the non-relativistic Schrodinger wave equation, and if you put all your information in here, you can come up with the orbitals, like the 1s, and here's the 2p, and here's the 3d, and here's a 4f. But there are variables that go into this equation, and we've already seen one of those variables for sure, n. When we said level, n equals 1, level n equals 2, 3, 4, 5. Okay, that's one of the variables that goes in that equation, and that is called a quantum number, the principal quantum number. But there are 2 more. There's L and there's M. So those are also variables in some big equation that we hopefully will never look at, certainly not in AP. So the quantum numbers have kind of a simple idea behind them. Okay, 1, the principal quantum number, the distance from the nucleus. So we're talking about, what floor are we on? So n equals 1, first floor. N equals 2, okay, second floor is, obviously higher up than the first floor. Third floor is higher up than the second or the first. Fourth floor is even higher. What that means for our orbital is that the electron spends more time farther from the nucleus. So each one of these, on the average, as n increases, the electron spends more time farther from the nucleus. The L quantum number has to do with the shape of the orbital. In fact, there's a direct correspondence here, and that is when L has a value of 0, then the shape is an s orbital, okay, where there is no angularity to it at all. It's just you go out any direction. Okay, when you get to a p orbital, then it's along the x, y, and z. When you get to the d orbital, L equals 2, and when you get to the f orbital, L equals 3. So in that equation, when n equals 4, then it turns out that L can have any value from 0 to n minus 1. So it could be 0, and that's an s orbital. It could be p, it could be d, it could be f, when L equals 3. So that's why when there's n equals 4, there are 4 possibilities for L. That's why there are 4 different types of orbitals. When n equals 3, okay, that's why there are 3 types of orbitals, because L has values of 0, 1, or 2. When n equals 2, there are 2 possible values for L, 0 and 1. That's why there are two types of orbitals. And when n equals 1, there's only one value for L. It has to be 0, so there's only one type of orbital. The third one, okay, the m quantum number, has to do with, what's the orientation. So if we say p orbitals always come in threes, why are there three orbitals? Because when you get to m can have any value from negative L up to positive L. So let's say that L equals 1, then m could be negative 1, 0, or positive 1. When L equals 2, negative 2, negative 1, 0, positive 1, positive 2, 5 values, 5 orbitals. L equals 3, there are 7 possible values, that's why there's 7 orbitals. And even back here when we're talking about when we have an s orbital, L equals 0, there's only one possible value for m, and so that's why there's only one orbital. We don't have to spend a lot of time worrying about quantum numbers, but the idea of quantum numbers, are there, and they kind of help define, why is the pattern 1, 3, 5, and 7, if you were interested in that. So finally, putting it all together, we're saying for a hydrogen atom that when we see that red line, okay, that red line came because the hydrogen electron went from level 3 down to level 2. Well, what does that mean? That means that the electron was somehow in some sort of a wave pattern in the third level, so maybe the 3s wave pattern, and then maybe it dropped down to the 2s wave pattern. When it dropped from one wave pattern to the other, changed from one wave pattern to the other, it released some energy, and the energy came off in the form of red light. Now, if it went from 3p to 2p, then that would also give off red light. If it went from 3D to 2P, that would give off red light. So anything from 3 to anything 2, okay, would give off red light. So there'd be a lot of ways it could do that transition. In the same way, if we're talking about the blue-green line, okay, here from 4 to 2, then anything 4, say 4S down to 2P, or maybe it went from 4D down to 2S, or it could be 4F down to 2p, anything 4 to anything 2 would result in a blue-green line. And the same way for the purple line, okay, 5 down to 2, something 5 down to something 2. And that's how we see what's going on in the hydrogen atom.